okay? Awesome. Good evening. Welcome to our Naturally Speaking series. My name is Rachel Reesbeck, and I'm the Education Director for the museum. I'm really excited for tonight's talk. We actually was introduced to our speaker through a comment on social media. And so posted about our planetarium, and then our speaker was like, oh, I went there when I was a kid. It's really inspired me to where I am today. And so, of course, our marketing team really, they glommed onto that. They were like, oh, we like that, we like that. But we all here at the Virginia Live Museum have a very similar story. I came here as an elementary school student, came here when I was in high school, volunteered here right out of college, and then eventually came back here later in life. So I think a lot of us can really feel that connection to our speaker. We thought it was a great opportunity to bring him here and share all about his work. So I want to introduce Dr. Michael Rutkowski. He is our speaker for this month. He's the Associate Professor of Astronomy at the Minnesota State University. So I'm going to turn it over to him. Enjoy.
Thank you.
You're welcome.
So I think I can stand. I'm not very good at lecturing at a podium, so I'm going to try to stand to the side. I may have to jump back and forth, but if anyone, I think this is what's amplified. If I am not holding this close enough, just like signal me and I'll try to reset. So I'm going to try to cover. I was told I have to do this in 30 minutes. I will not be able to do this in 30 minutes, but I know we have an hour, so I'm going to eat a little bit of your question time, but I'll make it worth your while because we're trying to cover a century of astrophysics in 30 minutes. And so, well, let's just jump in. Well, the parenthetical statement there just below, just to give you a little bit of background. I grew up in Middlesex County in Urbana, Virginia, home of the Oyster Festival, if you've ever gone up north to that. I have friends here that I've not seen for about 30 years, probably 20 years, whose daughter was about a decade older than I was my babysitter. And Urbana is a small town, about 600 people maybe, 500 people. And we have 2 PhD astrophysicists who grew up in that town. And one was my babysitter, and I'm the other one. So there's something in the water in Virginia, or at least in Urbana. And that's what the parenthetical statement is. So Chesapeake, of course, is the Great Shellfish Bay. And I've moved all over the world. I've lived in a lot of different amazing places. But I now live in Minnesota, Makoshe, which is the Lakota word, Lakota word for the land that reflects the sky, because we have all these lakes and they never have any waves. I haven't had tides forever, but that's the parenthetical statement if you're wondering where that comes from. So anyway, let's jump into it. I'm going to try to cover 3 big questions, which is wonderful that we get to do this in my line of work. We get to ask one-word questions. What or why is such a thing the way it is? I'm going to try to cover the definitions of these 3 terms, stars, galaxies, and universe, in 30 minutes. And each of these questions was unanswered a century ago. We simply did not know what a star was, we didn't know what a galaxy was, and we didn't know what the universe was composed of. In the past century, we have constrained those dramatically, primarily with observations and theory obtained with ground and space-based telescopes. So what's a star? Before we get to the nature of the star, I teased in the abstract that there was a Virginia connection here. So this is John Draper. John Draper was actually a very wealthy, I think, Englishman who moved to the US. I think he had a chemistry background. And he was famous for taking the first photograph of an astronomical object. So they invented the camera. People took pictures of people at the park. He decided, let's take a picture of the moon. So here's a daguerreotype that he took of the moon. You can see the outline here of the moon. There's a shadowed region on the other side. But he was a professor for 1 year at Hampden-Sydney College, where I happened to get a scholarship to go to. I would have never been able to afford it otherwise. But this was the old college. This is now a dormitory. My dorm, actually, my freshman year was right there above that windowsill. And he was a professor here. So for a year, he probably taught chemistry classes in the top floor. He had a laboratory, we believe, in the top floor. I asked the historian, they didn't know exactly. But the more interesting connection to Prince Edward County and the story of astrophysics is that he had a son, and his son, Henry Draper, was one of the founding great-grandfathers, if you will, of modern astronomical observing. So he took pictures, he tried to one-up his father. His father took photographs, but he took spectral photographs. So he put a prism in front of the light, dispersed the light on the camera, and we got this sort of rainbow pattern. Now, he wasn't the first person to do this. Here's the rainbow pattern that you've probably seen when you've seen a rainbow. This spectrophotograph, this is actually hand-drawn by Fraunhofer, who was and the top image shows you, or the bottom image is what's familiar to you. Red through blues are dispersed in this horizontal direction. And if you compress this into one dimension, an astronomer would call this a two-dimensional spectrum. This one-dimensional spectrum is going to come up later. So all we've done to create this image is to compress the intensity of light at each wavelength into a single, functional form. Along one axis, we just collapsed this image into one dimension. He was very good at building photographs that could obtain images like this. So we no longer had to, this is pastels, this is hand-colored spectral photograph. But he took his father's cameras and his chemistry knowledge of how to develop the solutions and whatnot, and he started taking photographs of stars. And his first image of a spectrophotograph of Vega, one of the brightest stars in the summer sky, in the summer triangle, is here. And you see it's a black and white image, but you see in the intensity of light here, the white lines are where it's an inverted image. So white is low intensity, black is high intensity. But this was the first spectral photograph of Vega. Now, he died, as people do, and his wife was collecting all of these glass plates. You guys are of a certain age, probably. You remember taking a photograph. The photographs used to be printed on glass plates, and she had a garage full or something of these glass plates that he had obtained over his lifetime, making these observations, and she collected all these after his death and said, where are we going to put these? Harvard, they were living in Massachusetts at the time, even though he was born in Prince Edward County. They went up to New York, then up to Boston. He married this very wealthy woman, and she decided to donate all of these to the Harvard College Observatory, which at the time was like the only observatory that was really producing science. And so that really started off the Harvard College Observatory's archive of spectral photographs. He donated these, or she donated these to, getting ahead of myself. So here's the photograph. I want to explain briefly why these lines are here. This won't be a science-heavy talk, but I do want you to come away learning a little bit more about the meat of what we do with these data, not just pretty pictures. So imagine an atom. Here's the simplest atom you can imagine. Here's hydrogen atom. You probably remember in elementary school, there's the nucleus of the atom, and that's orbited around by these electrons. And those electrons have a charge, the negative charge. The nucleus is positively charged. There's an attraction that holds that electron in orbit, just like planets orbiting around the sun. But unlike planets orbiting around the sun, these electrons can only inhabit certain orbital levels, what we call the principal quantum numbers of these atoms. So it can live at n equal 1 in its orbit or n equal 2, but it can't leave at n equal 1.5 or 1.72. It can only exist between those two states. Now, as you know, in order to take an elevator to ground 2 or level 2 or level 3, you need to do work to lift you up. So when the electron moves between these orbital levels, work has to be done or energy has to be transferred. And the way that the universe keeps track of how energy is moving through a system through electrically charged material is by the transmission or absorption of a photon, a particle of light, a little packet of energy. And so if this atom is exposed to sunlight or light of any sort, it will, here's my photon. If the energy of that photon, this little wave or particle, is exactly equal to or greater than the difference between two of these energy states, this electron will hop up to the next excited state. Just like it takes, I always explain to my students, if you want to walk up the stairs to the second floor, you have to eat a candy bar first to get energy to go up to the second floor. So it absorbs that energy. But if you're looking at this system, if there was a light bulb over here that was producing this light, and it was absorbing that energy, then as you're looking at that light bulb, that specific energy, that specific color, that specific wavelength of light would not be seen to your eye. So when you don't see light, it's dark. So that's where we get these dark absorption lines due to the transition of electron and an atom in that absorbing gas, removing that energy from the system. Now, that's an unstable configuration. If we remove this floor from beneath us, we would fall immediately to the ground state, to the the lowest potential energy zone. Electrons follow the same behavior. In the primary transition, the 2-to-1 transition in a hydrogen and atom from 2 to 1, the lifetime of that excited state is like 10 to the minus 7 seconds. So for a 10 millionth of a second, the electron sits at that state, but it immediately falls back down very quickly. And when it does, it will emit a photon with an energy equal to the difference between that system. So if you're or the difference between those two states. So if you're looking at this system, and this gas is now losing energy, it's going to radiate away the energy associated with that state, you're going to see a particular photon of a particular color or wavelength of a specific energy radiated away. We call that an emission line. So this would be an absorption line system, and this would be an emission line that would be produced. So that's where those lines come from in the system. And so his wife, Henry Draper's wife, donated to the Harvard College, and I won't have time to go into this story. It's a really good story about what the Harvard College computers were doing. They weren't computers, they were human beings. And I'll tell it. Pickering got really frustrated with his male graduate students at Harvard because they weren't getting the work done that he needed done on obtaining the spectral photographs. And so he said, I don't know if it's apocryphal or not, I should look into it a little bit further, but he said, my Scottish housemaid could do a better job at classifying and organizing all this data we've been collecting in our observatory than you guys can. And probably someone said, well, then hire your Scottish housemaid. And he said, fine, I will. So he hired his housemaid, a Scottish woman named Wilhelmina Fleming, and she went out and recruited a bunch of other women who were very interested in doing science, but it was the 1900s and women weren't allowed in the observatory. So the next best thing was to work in the archives of the observatory. And they started to classify all these spectrophotographs, many of which have been donated by Henry Draper's estate and then obtained on their own from Cambridge, Massachusetts. And they discovered a few things. First of all, they found that the sun, when we looked at its spectrum, it had similar spectral features to many other stars. Our sun was not a unique system. There were many other systems out in the universe that looked the same. And they also found that they could be classified in terms of their temperature, that stars weren't all the same temperature, that the surfaces of stars ranged from anywhere from a few thousand Kelvin or a few thousand degrees up to 40,000 Kelvin or hotter, we now know. But what they didn't know is what these systems were made out of. They could identify the elements, but they couldn't identify the abundance of the elements. So they could see hydrogen, they could see oxygen, but they didn't know how much oxygen or how much oxygen relative to hydrogen were there in the stars. And that solution comes from this individual. In exactly 100 years ago, she published, Cecilia Payne-Gaposchkin, published her dissertation on the atmospheres of stars, in which she took these data that had been classified by the Harvard College computers and applied physics to those data to understand what were the abundances of the elements in these stars. And the reason I say, you could argue, there's very rarely one time in history that you can point to that there's a transition made in the field. But in this case, before this point, we were doing astronomy, the classification of objects. This object's brighter than this one. This object's bluer than this one. But we didn't know why, because we weren't applying the physics yet to understand why is this one blue, why is this one hot, why is this one so massive, so on and so forth. She was the first person to apply that. It was such a good dissertation, they had to invent the PhD program to give her one at Harvard. So she was the first PhD at Harvard College Observatory, and I would argue that she was the mother of modern astrophysics, the application of physical principles to understand astronomical observations. So here's a modern spectrum. This is a 1D spectrum of the sun. It's a little bit more complicated now, just to emphasize where the progress was made from what Henry Draper was observing. So just imagine this axis is the intensity of light or the brightness of light. And you'll notice there's a curve, just like that hand-drawn one from Fraunhofer in the 1880s. But then there are these dips, and these dips are labeled. These are called the Fraunhofer lines because he identified these darker regions where there was less light than this overlying curve. And those lines, we knew from laboratory experiments, were associated with certain elements, calcium, iron, hydrogen, so on and so forth, that we had isolated, heated up in a lab, and allowed to cool down and emit radiation. The presence of this line alone, though, the depth of that line, you might say, well, if it's really, really deep, then there must be a lot of stuff to absorb that light. But that's not necessarily true, because not every atom can absorb every wavelength of light at this, or not all of these wavelengths of light. And so what Cecilia did to solve this problem was to apply the physics. So to understand how she applied this physics, I'm going to give you an analogous example. Because it's April. Imagine the worst April Fool's joke that your friend could play on you. They give you a big bowl of colored candies. Some of them are M&Ms, but some of them are Skittles. And if it would be miserable to dive into that bowl and try to grab a candy and expect the sweet chocolate and instead get the tart of the Skittles all mixed together. That's a horrible flavor combination for me. So what I would do as a physicist is try to estimate what's the probability that when I reach into this bowl that I'm going to pick up what I think is a green M&M, but in reality it's a green Skittle. And so what's my chances of having a bad time with a handful of candy? So to do that, you could do this math yourself. Just so that it looks fancy, we'll just call this psi total. This is going to be a fraction. We can assign it any variable we want, but we want to get at what's the number of green M&Ms in that bowl to all the candy in the bowl. That's the number that we can use to estimate the probability of having a good handful of candy or not, mixing the two flavors together. To calculate that, it's pretty, you probably can guess what you would need to do. What you would first need to measure is, what you would need to know is the number of M&Ms in that bowl relative to all the candies in that bowl. But then not all M&Ms are green M&Ms. If I really want the green M&Ms, because those are my favorite color of M&M, I need to know the fraction of green M&Ms to all M&Ms. And M&Ms come in reds and greens and blues and browns and so on. So it's really just the multiplication of two ratios of numbers. And from that, you can get a sense of what's the likelihood that I'm going to grab a green M&M from this bowl, given that there's other things scattered within that. So I take that to stars, and that's what Cecilia Payne did. So what we knew is that the brightness of a given line, or the strength of an absorption line, varied as a function of the temperature of the star. So for hot stars, twice as hot as our own sun, hydrogen lines were very prominent. So the strongest lines appear in the A class of stars. That makes sense. A class would be the strongest line, B class would be slightly fainter, C class would be fainter still. We rearranged those because the Harvard College computers realized it's a sequence in temperature. So now we have this famous sequence we still use, but it starts O, B, A, F, G, K, M, because it turns out the O stars are actually the hottest, the B stars are next hot, so on and so forth. But the point being is that the intensity of hydrogen is going to vary as a function of the type of star, but the variation in the absorption strength of hydrogen, how deep that line is, how prominent that absorption of hydrogen is not due exclusively to the presence or not of hydrogen, but the temperature of that gas in which the hydrogen sits. Because in that gas, if the temperature is very cold, if you're looking for a specific absorption to occur between, say, the n = 4 and the n = 2 state, in order for that absorption to occur, you have to have a lot of electrons first hanging out in the n = 4 state that can drop down to the n = 2. But if the gas is really cold, most of those electrons aren't going to be excited to begin with. They're going to be hanging out closer to the n = 2 or the n = 1. So that line is going to appear very weak. There may be a lot of hydrogen in that system, but you won't see a strong absorption because you don't have the right number of electrons in the right positions to make that transition occur. Alternatively, if you have a really hot gas, when you expose atoms to high energy, you can liberate the electrons. In a hydrogen atom, which has one electron, if you kick that electron off, there's no transitions you're ever going to see because there's no electron bound to that atom that can bounce up and down between the two. So there's a trade-off. There's a balance between the state of the electron and the state of what we call the ionization state. And those were independently, the way to calculate those as a function of temperature, were independently derived by Meghnad Saha, an Indian astronomer, and Ludwig Boltzmann, a Swiss physicist. Saha and Boltzmann, 40 years prior, less than 40 years prior. But what she said is we can combine these two together to figure out what are the fraction of atoms that can absorb at a particular energy and therefore produce the emission or absorption line that I'm observing in the spectrophotograph to all atoms in the emitting region, all atoms in the atmosphere of a star. And when she did that, she realized two very important things. One is that, here's table, what is that, 28? Page 184 if you want to look it up. I just took a screenshot. This is the abundance of atoms that she measured applying this technique in stars. And I'll just call out, for example, hydrogen and iron. This is logarithmic, so for 10 to the 11 here, and iron 10 to the 4.8. For every million hydrogen atoms, there was one iron atom. And so for every 10 to the 11 hydrogen atoms, there are 10 to the 5 aluminum atoms. And this, if you compare, so stars, first of all, the most prominent abundant species of atom is a hydrogen atom, and to a lesser extent, helium, and then trace amounts of everything else. But if you compare that to things that you find on Earth or the meteorites that people had already picked up over the past century and were examining in laboratories, the abundances were very, very different. And I'll call out here again, iron. In the sun, the stellar abundance is very low. On Earth, if you integrate the whole Earth, we have this very dense iron core in the center of the Earth. The abundance is sky high. There's so much more iron than there is in the Earth than you'll ever find in the interior of the sun or the atmosphere of the sun. And that's true for almost all elements. Whereas the sun is primarily hydrogen and helium and nothing else, 0.1% of everything else, that ratio doesn't come anywhere close to what we see on the stuff that we can pick up on the Earth. And this was a huge revolution because prior to this discovery in her dissertation, people assumed, well, the solar system formed together, the sun and Earth and moon and the planets all formed from the same primordial gas. Therefore, they should all probably have similar compositions. So we go out and we look at a rock and there's pyroxene, there's oxygen, there's silicon, there's nitrogen in the atmosphere. And we would expect to find similar proportions in the sun. In reality, that wasn't the case at all. The sun is a vastly different composition than all of the rocky material that we find. And even compared to the ice giants and the gas giants in the outer solar system, vastly different proportions of heavy elements. And for an astronomer, a heavy element is anything heavier than helium because most of the universe is just hydrogen and helium. The rest is just rounding errors on those abundances. So those were her big discoveries. And that set in motion, I think, the story of astrophysics. Now, question 2 was, what is a nebula? Here's a nebula. Nebula is a Greek word for cloud. We were looking out at the night sky, we were cataloging stars, and then every so often we'd come across something that was fuzzier than everything else. So we called it a fuzzy object, but we wanted to be fancy, so we called it a nebula, okay, instead of just fuzzball in the sky. Here's one of the famous fuzzballs. This was discovered with this telescope. I took my mom to see this telescope because that's what you do when you want to go on vacation as an astronomer. This is the Leviathan. This was once the largest telescope in the world. There's a me for scale. It was a large mirror, but it had no camera attached to it. It didn't have a computer. This was a hand-drawn sketch. Someone sat at the end recording what they saw as an artist. We saw these objects, we cataloged them. This is where the Messier objects catalog came from, these fuzzy objects that weren't comets and weren't stars. But we didn't know what they were. The person who resolved that question for us was this individual, Edwin Hubble. In 1929, he published on the realm of galaxies, on the realm of nebula, in which he determined that there were generally two classes of galaxies. There were round, boring football or basketball-shaped galaxies, and then there was a more dramatic spiral galaxy sample, some of which had bars, but in general, big, sweeping, broad arms and round M&Ms in the sky, if you want to think of them that way. And he measured the distances of these, and he realized these are not part of our own galaxy, the Milky Way. These are separate and distinct island universes, he called them. They are separate and apart. They are the closest massive galaxy to our own is on the order of a million parsecs, 3 million light years away. So when you see it in the night sky, you're seeing it as it existed 3 million years ago. That's the closest massive galaxy to our own. These were not, as some people argued, part of our own galaxy. And so in one fell swoop, we realized that the universe, which up to that point was probably, we thought was just the size of the Milky Way galaxy in which we lived, was actually much, much larger than we ever imagined by Edwin Hubble's work. Now, this is what I've focused on most of my life, is the study of galaxies and galaxy evolution. I won't talk too much about it for sake of time, but when you think of a galaxy, these are the two types of galaxies that Hubble classified. So you have these boring, round, elliptical galaxies, which I've spent my entire life studying because no one else wanted to study them, but I said there's got to be something interesting going on here. And then when you think of a galaxy, you think of this pinwheel shape or these broad spiral arms. These haven't been doing much, if anything, for billions of years. They're not forming new stars. They don't have much cold gas from which to form new stars. These are chock full of gas. These are forming stars at anywhere from a few to tens of solar masses per year on average. These were the two classes that he saw. But as we built better and better telescopes, like the Hubble Space Telescope, now James Webb, we get these new images of galaxies, and we find that not every galaxy nicely fits into the dichotomy that Hubble identified. So we have all these galaxies that look like train wrecks, for lack of a better word. What happened here is this was once a nice little spiral galaxy. This is called the Penguin Galaxy for reference, because there's a little egg and the penguin watching out over the mother of the egg. This galaxy has, in fact, collided or passed very close to this other galaxy, and it's caused, because of the gravitational interaction, it's caused the galaxy to distort its shape. And so over the past 50, 70 years or so, what we've really been interested in galaxies, not just classifying their shapes, but trying to understand, by the application of physics, why do the shapes appear as they do? Why is this galaxy shaped this way? Why does this galaxy, if you'll notice, there's all these little clusters of red dots. These are star-forming regions where stars are forming at hundreds of solar masses per year. They're pouring out new stars. There's new stars coming into existence every day, averaged over the past million years or so. Why do these occur in these galaxies, but we don't find them in other types of galaxies? To answer that question, we apply physics. So this is the astrophysics of galaxy evolution. This is a paper, actually, it was published just this Friday. I got the notification in the Astrophysical Journal. These are some of the galaxies that I look at. Remember I said I look at the boring red galaxies. When we look to the distant universe, this is Hubble imaging. The galaxy that I'm interested in is right in the center. We still find similar galaxies that we find locally, but there's a greater diversity. There's many more train wrecks and colliding galaxies and mergers of systems. And my question has always been, well, what is the role of those galaxies in the vicinity on the evolution of that boring galaxy in the center? And to do that, we really need space-based telescopes or large surveys. I'm also a member of a number of programs with the James Webb Space Telescope, which was launched just 3 years ago now. This is, I hope it plays, this is just a little animation. Yeah. In the center of this image, you're going to see a bright spot or a bright area. That's a galaxy, but you're looking at a galaxy as it looked about, on the average, these were all selected to be at about 10 billion years ago. So we're looking at them when the universe was about 2 billion years or 2.5 billion years old. And they look, of course, very different. Some of them are still kind of compact, but the only reason we can see them is because they're alight with star formation. So they don't look anything like the red dots that we find locally, or the red galaxies we find locally, which don't have any young stars. These are 1,000 solar masses, 10,000 solar masses of stars are being produced on average each year within these systems. So the morphology of these galaxies changes dramatically, but they all exist in the same universe. And the physical laws that apply here apply on the other side of the universe as well. And so what we can do is apply those laws. We will never see galaxies evolve forward in time because no one will ever get funding to wait 1 billion years for a galaxy to evolve. But what we can do is, it's sort of like a yearbook. Everyone in the yearbook in kindergarten is going to end up in their senior year. You don't know what that individual kindergartner is going to look like in 12 years, but you can look at the high school seniors, and you can look at the way that they cut the hair, or how many teeth they have, or whether they have scars or not, and you can figure out over the next 12 years, what's the likelihood that students will grow a beard or whatever. So you can apply that same principle to these systems. And if you look further and further back in time, because the speed of light is finite, you're able to see earlier and earlier in the history of the universe. And we can put these dots together, not link the chain, not for any one individual galaxy, but for the ensemble population of galaxies. We can try to understand, how do we get the big red boring galaxies locally? Well, we know what they looked like when they were babies. So what physical laws, what had to have happened over their lifetime to give rise to the ones we see today? And so that's really what I study. I spent most of my time studying. Now I'm going to call out one thing in particular because, well, there's no really terrible young people, but sometimes when you go to a talk like this, the person says we've solved everything, and then you get really disappointed because you think, well, what am I going to do if I get a PhD in astrophysics? We haven't solved galaxy evolution yet. There's one really big problem with galaxy evolution in my mind, which I'm going to highlight in the next few slides. So first of all, stop and appreciate the fact that we can write in one slide the entire history of the entire history of the universe in a cartoon. This is a timeline. This is where we are today. At the beginning of the universe, there was a Big Bang, after which all that has come into existence today was born. It took a long time, about 400,000 years, plus or minus 10,000, for the galaxies, the first galaxies, 200,000, for the first galaxies to start to form in this universe. For the first few 100,000 years, that's the realm of Thomas Jefferson Labs down the road. The high energy universe, where there weren't stars, there weren't galaxies, there weren't supernovae. Nothing was happening except the production of protons and neutrons and quarks and so on and so forth. But at one point, galaxies formed under their own gravity, and they've been evolving ever since to the present day. So this is pretty amazing to me that we can write this down. Let me just say that because I know you're recording. I don't want to watch this again and get it wrong. So this is about 200 million years after the Big Bang that the first galaxies came into existence. I think I said 200,000, but let's be careful there. So, okay. So the galaxies have been evolving ever since. We need to study these galaxies in the earlier and earlier times in order to figure out how to link the evolution of the population over cosmic time with these physical laws. And in that time, we've been able to push further and further back. Over the past century, we've looked further and further back in history in order to gain younger and younger galaxies to study for galaxy evolution. In 1925, the universe was one galaxy. We thought the Milky Way was when Cecilia wrote her thesis, that there was just the one galaxy, the Milky Way. In 1929, Hubble realized that's not the case. There are many galaxies out there. There are many independent island universes out there. But we were limited to the ground, basically, for observations, and we have to build really, really big telescopes to see really, really faint objects far away. So it wasn't until the 1960s or so that we started to look at even a billion years back in time. And this wasn't even in the optical. This was largely in the radio and then following up in the optical. So 1963, we pushed back to about a redshift of 0.1, or about a billion or so years back. By a particularly auspicious year, by 1985, when I was born, we were looking at galaxies about 4 billion years ago. And then in 1990, when I was in kindergarten, we launched the Hubble Space Telescope, and we started to be able to identify galaxies at very great distances. And by 2015, the most distant galaxy we had observed was about 500 million years after the Big Bang. It wasn't the first galaxy to form, but it was amongst the first. And we built Hubble we launched Hubble in 1990. For 30 years, for my lifetime, it's been doing wonderful work, but it's a relatively small telescope. And the light that's produced by stars that we use to identify the galaxies in distant universes is being stretched as the universe expands, I'll get to that in a second, into the infrared wavelengths. So we had to, if we wanted to push back even further, we had to build another telescope that operated not in the optical or ultraviolet, but in the infrared, longer wavelengths than you can observe with your eyes, your naked eye. And so we launched JWST, and in the past few years, we've really pushed back. There was just an announcement this year of redshift 14, which corresponds to about 250, 280 million years after the Big Bang. We're almost at the very beginning of the first galaxies. We have not discovered the first stars to form, but with JWST in the next few years, I suspect that we will. But over a century, we've gone from knowing there was one galaxy to being able to probe just a few 100 million years after the Big Bang, which is about as far back as we can probe to look for stars, because before that, there were no stars. There were only naked little protons and electrons running around to make hydrogen eventually. So The big question that remains, though, oh, I guess I should summarize. What we now know is that galaxies evolve as a result of very dramatic processes, both in situ, internal processes. They build these giant black holes. These giant black holes at their cores burp out radiation and energy and inject energy into the system. That can destroy clouds, molecular clouds that would go on to produce new stars. They can kill themselves from the inside out due to their rapid formation. We also know that merging is prevalent, that galaxies merge together. Our own Milky Way galaxy will merge in a mere 4 billion years with this closest galaxy, the Andromeda galaxy. And when it does, we can say with a high degree of certainty, we can predict the future 4 billion years from now, and we know what that galaxy is going to look like. When the spiral galaxy of the Milky Way and the spiral galaxy of Andromeda merge, we know there's going to be produced one of these giant red boring galaxies because we can study that process of merging over now 13 billion years of cosmic history and connect those dots. So that's what we've learned, but the big question that remains unclear is galaxies not only are dismembering themselves and colliding with one another, but they also have an impact on the broader universe. And something very curious was discovered in the past, well, over the past 80 years roughly, in which we realized that when you look at the gas between galaxies, not bound to galaxies, but gas that sits in between galaxies, which is primarily hydrogen, the most abundant element in the universe, we never found it as hydrogen. We always found it as a proton and an electron. They had been separated, which means something has to be producing enough light or energy to kick those elements or those constituents apart and keep them apart, because if they recombine, they're going to make hydrogen, but we don't ever see it. So some field of radiation is out there disrupting what we call the intergalactic medium, the space between galaxies. Now, the theory is that, well, you have stars, and stars can be really bright at those wavelengths. They can produce a lot of that radiation that separates the electron from the proton in a hydrogen atom. Maybe all of that light from these galaxies that are forming stars at tens of thousands of solar masses per year, maybe that escapes into the IGM, the intergalactic medium. The problem is whenever we look for that escaping radiation in the ultraviolet, we never find it. Or, at least until about 15 years ago, coincidentally, the time when I first started to look at it, which I'm not going to lay credit to that, but to show you what this looks like, what we're looking for, the radiation, the impact of this radiation, here's a constellation that you might recognize. This is Orion upside down. You might see the belt of stars there, Mintaka, Betelgeuse, Rigel. And then just below it, just below his belt, you may have seen in a dark sky, hopefully you've seen in a dark sky, you're amongst the lucky ones if you've seen this, there's that cluster, that little fuzzy blob, what we call M42, Orion's Nebula. If you zoom in on that with a space-based telescope, oh, just for reference, if we didn't have, this is something I like to point out because people think the stars don't really matter to us, they're just distant points of light. But this cluster of stars here is churning out so much ultraviolet radiation that if we didn't have the ozone of the Earth, when you went outside, you would get a sunburn at night from this cluster of stars. That's how much radiation it's churning out. Now, if you zoom in with a space telescope, here's what it looks like. In fact, it's a really wimpy cluster. There's a single O star, which is the hottest classification of stars, and there's a handful of B stars, slightly cooler. There's a couple stars that are like 30,000. There's a couple more that are like 15,000 Kelvin, so 5 to 6 times the temperature of our own sun. This is what it looks like. And what you're seeing here, this beautiful nebulosity, the colors here are due to either transitions in bound atoms, electrons bouncing up and down, or recombinations. So the ultraviolet has kicked out the electron from its host atom. Eventually that electron finds its way to a new atom, it recombines, and it falls back down to its ground state. And as it does so, it emits all these different lines of radiation that we see in the spectra, in emission rather than absorption, as it falls back down to the ground state. Now, for reference, if you've been to the southern hemisphere, you might be a little bit more familiar with this region. This is called 30 Doradus in the Magellanic Clouds. This is the closest external star-forming region to our own galaxy. Looks very similar, but to give you a sense of scale of how much UV is being produced and how much ionization and reprocessing of the medium is occurring, I've also plotted, maybe you can see it, the Orion Nebula. Can you see the Orion Nebula in there? All right. This is the Orion Nebula on the scale of what we call 30 Doradus, or the Tarantula Nebula. It's the same physics. The ionizing radiation, the radiation that kicks the electrons free, is pouring out from the host stars that are produced in the star-forming region, and it's consuming, it's eating away, it's boiling away, if you will, all of the neutral gas around it in its birth cocoon, if you will. The idea is that, well, if this region is producing so much ultraviolet radiation, then surely some of that ultraviolet radiation can ionize a whole bubble around it and then eventually escape out to the intergalactic medium. The problem is, as I'll show you in the next slide, we never find it, or we didn't find it. So this is just a collage of 15 years of my work in astrophysics into one slide on this topic. So we've used ultraviolet telescopes like GALEX, which is now defunct, deorbited a few years ago. The Hubble Space Telescope also has ultraviolet capability. And what you see, it looks like well, maybe you're not from, if you're of a certain age, you'll remember the snow on the static on a TV screen. It just looks like static. If these galaxies were producing ultraviolet radiation, which was escaping into the intergalactic medium, there should be a bright white point in the middle where that crosshairs is. There's nothing there. So when we looked for it in galaxies where we could find it, it never showed up. Now, in the past 10 years, we finally convinced the Hubble, what we call the TAC, the people who allocate the time to the scientists to observe the targets they're interested in. We finally were able to convince them, can you please spend orbit after orbit staring at these particular objects which we think are good candidates? And we're starting to find real detections. Once you see error bars on data, that means we found it. So we're able to find the detection of this escaping radiation. But the problem is we still don't have enough of these galaxies in the high redshift, the distant universe, in order to produce the reionization signal, or the reionization event, or that initial ionization that we observed 70 years ago. So there's still room for discovery in this space. We're not there yet. So we're about, well, I've got one more set of slides, and then can I go 10 more minutes? Or are you burning with questions already and I should stop? Okay, I'll keep going, and I realize I've given too much backstory for a lot of these things. But the last thing I want to wrap up saying, I'll skip the bit on what is the universe for now, but I do want to talk about Vera Rubin because it'll become relevant towards the very end. So we were studying galaxies. We were classifying them into these different shapes, these different types of galaxies with Hubble. We were finding that they evolved by collisions and mergers. All of this time, we had assumed that galaxies were what we saw. You know, we look at them in the ultraviolet and we see stars. We look at them in the infrared and we see gas and dust. That's what a galaxy is. In reality, galaxies are far more than what we actually see with our telescopes. And the person who nailed that down was this individual, Vera Rubin. So what Vera Rubin discovered, she meticulously modeled the orbits of objects in spiral galaxies around their center point. So imagine like watching Jupiter make a trip around the sun, measuring its speed and its orbit as it moves around the sun. We were instead watching stars move around the center of a spiral galaxy in Vera Rubin's work. And what you noticed, so here's the velocity here and the distance out from the center. And though we have different galaxies here, they all look similar. They rise very quickly in the center, and then they sort of plateau and they level out, and they become sort of constant. So a star that is 10 kiloparsecs from the center is moving just as fast around the center of the galaxy as a star at 20 kiloparsecs. It's a flat rotation curve. Now, what does that mean? Well, let's look at the rotation curve of our solar system. Here's a figure from a textbook. This is the orbital speed as a function of distance, same plot. The planets are labeled. Mercury, of course, is zipping around the sun at high speed. Pluto hasn't even completed an orbit since we discovered it. It's moving very, very slowly in its orbit around the sun. And the reason for that is because the distribution of mass in the solar system is largely in the sun. 99.9% of all the mass in the solar system is the sun. 0.1% is Jupiter. And everything else is that 0.00001% of the Earth and the asteroid belt and so on and so forth. And so if you look at the physics from Newton, actually, if the mass is constant, Oh, sorry, yeah. If the mass in the system about which is dictating the gravitational force that these objects feel, if that's constant, which in our system it is, there's a single mass in that system about which all the things are orbiting, then the rotational velocity would be predicted to drop as the square root of the radius. And if you think back to algebra class, this is sort of a square root looking curve. Rises at low values, and as you go to the extremes, it dips down to basically 0. That doesn't look anything like the rotation curves that we measured. But you can apply the same physical principles. If the rotational velocity is constant with radius, that implies that the mass is increasing with radius, the mass internal to that orbit. And so what this means is that as you move further and further out to the edge of a galaxy, there's still mass that's contributing to that velocity. It's not just all located at the center. The orbit of this star is not dictated by a single object in the center like in our solar system, but there's additional mass further out, which kind of makes sense. If you think about a galaxy, there's gas and dust that continues to spread out into the extremes of the galaxy. But what's really interesting is that if you go to the very edge of the galaxy, you're starting to run out of stuff that you see, and yet the rotational curve is still constant. So the mass is increasing with distance, but we don't see it. So matter, which is dark, we creatively entitled dark matter. And it turns out that about 90%, 50 to 90% of most galaxies is dark matter. We have no idea what it is, but it exerts a gravitational influence on the planets and the stars and the gas that we see making it their way around the center of the galaxy that we can measure. We know it's there. It interacts gravitationally, and yet it doesn't seem to produce a signature in the electromagnetic spectrum that we can detect with an optical telescope or an infrared telescope or what have you. And so that's that. Now, I'm going to skip this for the sake of time. If we want to use question time to talk about how do we know the universe is 13.8 billion years, then we can certainly talk about this. But just for the sake of time, I wanted to wrap up with a few philosophical points, and we'll come back to this. So bear with me. The future. So for you all, when you all go into astrophysics, the future is really big data. So the Europeans just launched, and I work on the NASA committee to make sure that, because we contribute 25% as the American constituency to the Euclid mission. So I work on the panel to make sure that Americans can at least use 25% of this spacecraft that we just launched. But this instrument, this telescope called Euclid, just released what we call the Quick Release 1 sample, which is 3 times this area. And if you zoom into any one of these areas, it's literally millions of galaxies, all shapes and sizes, all different masses, all different star formation rates and histories. It's a very complex data set. And it's not thousands or hundreds of galaxies, it's millions. In this summer, in July, the Vera Rubin telescope is going live in Chile, and it will produce every 3 nights, it will survey the entire sky that's visible. So in one night, it will produce 10 terabytes worth of data, or excuse me, 15 terabytes worth of data each night. Now, Instagram, all those photos we post on Instagram, is 10 terabytes per day. So there will be more data coming in from the sky than there will be that we posted in recipes and pictures at the Living Museum or whatever. Okay? There's a huge amount of data coming in, and there's nowhere near enough people to look at all these galaxies and classify these galaxies and measure their shapes and how fast are the stars moving around their center and all the interesting science we'd want to do. So the future is big data. Now, I'm going to skip Roman and come back to that later. But everyone in the field, it seems, maybe not everyone, but I'm certainly recognizing that if I want to do the science that I'm interested in with these big data sets, which are available to for everyone to download, then I need to be smarter about how I select my samples. I can't inspect every galaxy or run an automated classifier based on what I know about galaxies to find the galaxies of interest. Instead, I have to use machine learning, which is a word you're probably all familiar with. You all use it every day now, but it's directly applicable to this big data era that we're moving into in astrophysics. So I found a YouTube video. Some 10-year-old kid had figured out how to code up a machine learning software publicly available in order to identify apples and bananas with some confidence. It shows an image and it says, is this an apple or is it a banana? How sure of you are that? And I said, well, if we can do apples and bananas, then surely we can do big, boring red galaxies and beautiful spiral galaxies. And these are the ones I'm interested in. And if there's 10 million of them, and it has an error rate of 10%, let's say, of misclassifications, but it finds 100,000 of these that are accurate, that's a data set that I can start working my particular science on, but I would never be able to do that with millions. And so in preparation for a lot of this, we've been using what we call galaxy or universe in a box. We can apply these machine learning tools. None of these are real galaxies. We've just said what we know about the physics of galaxy formation and evolution, put that all into a simulation. Put that simulated galaxy into a cluster of galaxies, a big group of galaxies, and just let it run for 14 billion years of cosmic time. And what pops out? And you get these galaxies like this. I don't know if the resolution's good enough, but you see lots of big, broad spiral arms. And then the confidence of this classification is up top. So we can do this now. And I'm doing this with undergraduates now. You don't need to be an astrophysicist to train the computer, but you need an astrophysicist to help train the tools to make sure that you get the right type of galaxy that you're interested for your science. So with that said, I'm going to end on a sad note. And I promise this is my last spiel here. But we've gained a tremendous amount of insight. We skipped over the bit about what the universe is made of, but we didn't know what stars were. We didn't know what galaxies were. We didn't know what dark matter was. We didn't know dark matter existed. We didn't know dark energy existed. We've made tremendous progress. But in a century, we've also lost and are losing a tremendous amount. And because this is a conservation-themed talk, I thought it would be appropriate to just make a quick mention of some of the future that we're running into, the future implications of what we're doing now in space. So the first is, here's that image again of Orion's nebula, or Orion, the constellation. This was a photograph taken, like a 20-second photograph taken in I think it was Orem, Utah. I just found it online, a 100,000 person city or so. If you take the same photograph, same exposure, but in a dark site, this is what you see. We've all lost the view of the sky by living in the places that we do, from light pollution, and we always have to point out that light pollution is really pollution. Not only is it harmful to your health, I have some slides if you want to talk about the impacts of blue light on your sleep habits and your cortisol levels and whatnot, but it is pollution. No one flying a plane cares that they can see your backyard at night. That light that you put out for safety or something is supposed to illuminate the path so you don't trip on your way back from the car. It doesn't need to go up, but when it goes up, it prevents us from seeing the sky as it's existed for all of human evolution, but we've lost it with the advent of the light bulb in the past century or so. And it gets worse. We're entering into a world or an era in which it's very relatively inexpensive to launch lots of small satellites to low Earth orbit to do wonderful things. Some of these constellations have really noble aims: to deliver internet services to people in rural Saharan Africa so that we don't have to destroy the rainforest to put an Ethernet pipeline from the coast inward and allow these people to engage with the global community. That's a really noble aim. But the way in which the companies that say they're going to deliver this is not being done in consultation really with the astronomical community. And on the left, this is an image from the Vera Rubin telescope of a simulated image of what the field of view will look like with these constellations that are already in existence. These constellations of small satellites that operate sort of in chains moving across the sky. If you've ever seen a UFO in the past 5 years, it's one of these. You've probably seen this. At sunset, you sometimes see a trail of lights moving overhead. These are the Starlink satellites or some variation thereof. These are operated in a sort of a continuous order, beaming information about each one's position, and then transmitting information from the ground very quickly to space and back down. When we take an image, we're going to see them. And here's a real image. I think this was a minute exposure at Kitt Peak, I think it was, that I found online. If you want to study that little red boring galaxy in the background, but you have the bright streak of a Starlink satellite moving across, you can't study that anymore. It's been blocked. And there's only so many good nights to make the observation of that object because it's cloudy on the ground, or the object's not visible at that time of the year, or what have you. Now, Starlink right now is on the order of hundreds of satellites that have been launched in total. Here's a list of the upcoming mega constellations of satellites, small satellites to do various things. The largest of these will include hundreds of thousands of small satellites. Some of them aren't even designed to be dark. Starlink has taken some effort to paint the satellites dark so they're not as reflective on the ground. But some of these are designed to do nothing more than to put Coca-Cola in the sky and beam it and run the satellite train across a region they want to target with that advertising. They're not designed to be dark at all. When our sky is filled with hundreds of thousands of these, you will never know what a star is anymore, except for the fact that the ones that aren't stars are moving very rapidly across. But all of the scientists on the ground that have to peer through all this, we have to get really creative in how we extract the data where it's not contaminated, or we just have to give up. And giving up isn't really an option when it costs $10 billion to launch a James Webb Space Telescope into space. It's much easier to put a telescope in a mountaintop in Chile, or much cheaper. And that view is being incredibly restricted. Now, the last thing that I want to mention, and I added this slide in the last part, scientists don't get political or anything. We're oftentimes, we try to stay away from that. We hold our opinions to ourselves. But there was recently an announcement. As you all know, everything's in flux at the administrative level. Have you guys heard me the whole time? I'm just hearing. Okay. Okay. The recent budget proposal to Congress from the president, the administration, would have the effect of basically closing the Goddard Space Flight Facility. It would reduce the astrophysics division by 2/3. Now, you might think, well, there's a lot of government employees. Maybe we can find waste, fraud, and abuse, but it's in a division of NASA, which has a budget of something like $2 billion, to reduce it to $600 million means we're basically going to stop doing space-based astrophysics. Hubble Space Telescope will limp along until it eventually dies. It's on its last legs now. James Webb will be continued, but the Roman telescope that I said is launching in 2027, the spy agencies gifted us. This is how desperate we are for telescopes. They gifted us a spy satellite that was just sitting in a back room somewhere and said, hey, NASA, can you do anything with this? And we said, of course we can. It's a Hubble-sized telescope that we can do near-infrared and optical imaging and spectroscopy with. We've spent billions getting this up to speed for launch. In 2027, it's scheduled to launch, but that entire mission will be cut. The only missions for astrophysics are the ones in existence right now. And what NASA does, and I'll put it up here, which I don't think everyone appreciates necessarily, is NASA is not just rockets and moon landings. NASA is scientists developing and identifying new and important science to fund. It's a pass-through agency. I can point to, at every instance of my career, from Middlesex High School to faculty at Minnesota State, instances where I have been able to do something in a classroom that was made only possible due to a grant-making agency like NASA providing the funds to do that. All of that would go away. All of these talks would disappear, except for those who are rich enough to do it privately. But those private organizations won't ever come up with $10 billion to launch the next generation of James Webb. We can't convince Elon Musk to do that for us. So maybe for the little kids this is a little bit more relevant, but NASA it sustains that font of dreams. I think NASA is one of our proudest components of this American experiment, if you will. It is a place that we go to and we look for big discoveries to come out of. And we've had a century of big discoveries. There have been countless Nobel Prizes. There have been countless advantages in the marketplace that have been produced as a result of NASA investment in fundamental science. It's really the only way that we humans collectively can answer what I started with, these one-word problems. What, why, when? NASA does that. And because it's really expensive. It's really expensive to pay to build a telescope that no one has ever built before. People say, well, we've launched a rocket 1,000 times. But when the people who launched the Apollo rockets retired, there was no one who was building Apollo rockets in their backyard that could come on board when we needed the next generation to take us to the moon or to to Mars. And so it's really expensive to keep those people employed, to have them on new projects until the community in general says, you know what, we really need this piece of the puzzle. Can you set yourself to this again? So with that said, finally, I think I always say in my class that no one has a monopoly on curiosity. It doesn't matter the sex, the gender, the creed, the religious background, whatever. Everyone is curious. Everyone has wondered, why am I here? Where are we going? Why do things appear the way they do? These are fundamental questions that all humans... Now, some of us may stop asking these questions because, we grow up and we say those are childish questions to ask. We don't dream about things in the way we did when we were 6 years old or what have you. But we all ask those questions. And NASA is one of the few ways in the government that we're able to provide the ecosystem to let those questions grow into scientific experiments and knowledge that gets disseminated across the world. I've been on sabbatical this past year. I came back from Philippines a few months ago. Everything that I did with those students in high school, they have nothing. They had laptops. I mean, we had barely working electricity. The power would go off every day. It was raining in the buildings because the roofs were thatched roofs. And yet, all of them were so excited to be able to use NASA data that we provide as taxpayers to the whole world to try to engage people in the endeavor of science, because we know everyone's curious. Everyone has that spark at some point, and NASA is able to advance that. So I don't want to advocate in one way or another. I know this isn't scientists just aren't very good at doing this, but if you ever have a chance to run into some elected official, please tell them that, I went to this talk. There was a kid who was, playing in the mud in Middlesex County who was able to get a PhD because the science that he does was being funded for generations by organizations like NASA. And so I should have planned that speech out, but it was sort of thrown out of the. It was a bit of a curveball. Last week we were sitting at my aunt's house, and I get an email that says, "Can you guys start calling your representatives because we might not be here in a year." So on that note, I'll leave this quote up. This is from Cecilia Payne. Do not undertake a scientific career in quest of fame or money. There are easier and better ways to reach them. Undertake it if nothing else will satisfy you, for nothing else is probably what you will receive. Your reward will be the widening of the horizon as you climb. And this is what I've been lucky enough to do from when I was coming to the planetarium as a little kid from Middlesex when we used to go down to the Patrick Henry Mall for Christmas gifts. And now I always say, I'm the luckiest guy in the world because I get paid to ask, why is the universe the way it is? So I'll leave that as a point. And we have about 2 minutes for questions. So. It was actually, yeah. So I gave a little bit too much backstory, but if we have questions, I'll try to.
Any closer to finding what dark matter is about?
Excellent question. I'll bring up the slides that I had to cut out.
Nice segue.
We do. We are getting. Oh, sorry. I have to unskip it. The question is, are we any closer to understanding what is dark matter? So the answer is yes. So here's an image that came out with the Euclid first, one of the early press releases. What you're seeing here, this is one of those big red boring galaxies. But what you're seeing here in the center, you see this ring of light which has been zoomed in here. You see these multiple points here. This is the same galaxy at each point, but it's been lensed by the mass, a gravitational strong lens event. It's been lensed by the mass of the foreground galaxy. And so this is a really interesting, let me bring up the physics slide so that you don't have to take my word for it. So Newton, as we all know, Newton said gravity is a force that acts on mass. Anything that has mass interacts under the force of gravity. Therefore, an object with no mass will not be influenced by gravity. So light, a photon, has no mass. Therefore, when light passes near another massive body, Newton would say it just keeps continuing in a straight line. Einstein said, let's think about this totally different. Let's think of gravity instead as a manifestation of the amount of energy distorting the space-time field around it. In that case, the light will travel between point A and point B along the shortest path. If that path happens to be curved, that light will take a curved path to get from point A to point B. And so what you're seeing here is when we look at it, this is Hubble, but Euclid was the image that I just showed. A background object can be the light that is radiated in this direction. Instead of continuing off over here where there's no telescope to see it, if it passes close enough to this object, it will be bent. Now, you don't know it's being bent, so you would see this, you would trace this line back to a position here. So maybe this dot that appears for this background galaxy. The light that it was emitted here, if it passes close enough to this massive foreground galaxy, it's going to be distorted. And then tracing it back, it's going to be like this lower dot. Now, that's exactly what we see. We found hundreds of these lenses now. But to answer your question of, can we understand anything more about dark matter? The mass that distorts the light is only the mass internal to what we call the Einstein ring. This is the Einstein ring here. We can measure from the light, we can measure the stellar mass. How massive is the black hole? How massive are all the stars in that region? And we can compare that to how much mass would it take in order to make this shape. And when we do that, what we find is that in this core, the dark matter to light matter or normal matter ratio is highly biased towards the normal matter. There's a lot more normal matter than there is in dark matter. And you say, well, what does that tell us about dark matter? Well, what it tells us is that dark matter doesn't clump in the same way that light matter does. When you have protons, they tend to come together with electrons to make hydrogen. The hydrogens combine together to make hydrogen molecular clouds. Dark matter doesn't seem to do that. Even though 90% of this galaxy's mass is in the form of dark matter, when we have a lens, we can tell that the dark matter clumps in different ways. And because it clumps in different ways, we can then try to develop theories to explain how does dark matter clump at certain energy scales or whatever. And so we are making progress on dark matter. I think in my lifetime, there'll be a Nobel Prize for dark matter on its origin. There are lots of experiments to try to detect it directly. One of the coolest ones, I did a postdoc at Stockholm University, and in the basement, they had this big box. It was just a big metal box. Inside, they had E. coli bacteria, the stuff that's in your gut that makes you sick when it reaches your mouth. E. coli, the genome for E. coli has been sequenced. We know we can make it from scratch in principle. We can align all of the G's and C's and T's and A's together to make an E. coli if we wanted to. We can also clone E. coli very easily. We can structure the DNA in such a way, and we say, force this to make 1 million copies of itself. We did that, or not we did that. In the experiment, they did that. They cloned a bunch of E. coli with a known DNA. Now, DNA, when the objects reproduce, the DNA is going to change. It's going to mutate randomly. So some new pair combinations will appear. But we know the rate of normal mutations. But if we bury this object underground in a basement, we shield it so that cosmic rays from space can't interact with it. Light can't distort it. Like you can't get a sunburn, so it mutates in that way. Then what they did is after they let it sit for a while in this dark box, structured box, they said if dark matter has a certain mass, and we're being penetrated by dark matter all the time, we just don't see the interaction on our cells. But if the dark matter is massive enough, it will interact with the DNA, just like sunlight interacts with your DNA in the skin cells, and it will cause a mutation. So we know what the clone DNA looks like, so we siphon it all out, and we very quickly process the DNA chain and look for mutations that are above the normal mutation rate. And that indicates an interaction with some massive particle. But there's no massive particles that can penetrate into that box except for dark matter. So we're doing all sorts of wild experiments to try to figure out what the mass of dark matter, what's the energy. We're not there yet, but I do think that in my lifetime, we'll see a Nobel Prize for that.
A more basic question. So we got stars, and we got galaxies, and we got the universe. What defines the boundary of a galaxy? How do you know you left the galaxy and another one starts?
It's a So the question is, what defines the edge of a galaxy? How do you know when a galaxy stops? Like, you know what the edge of a star kind of looks like, right? You know what the edge of the Earth kind of looks like. Well, if you think about it, we really don't know what the edge of the Earth looks like. You know, where is the edge of space? You know, it's a very poorly defined. I mean, when these women went up in Jeff Bezos' private rocket ship last 2 days ago or so, you know, they went up to space. They went up to the Kármán line, or Kármán line. I don't know how to pronounce it. I only ever see it written. But that's at 100 kilometers up. But does space really start at 100 kilometers? I mean, the atmosphere is still fizzling out. The same problem applies to galaxies. There is a threshold beyond which the gravitational interaction of that galaxy with another would be minimal, so you could define that as a limit. But it's hard to say where one galaxy actually ends and the next begins, because especially when the galaxy itself is this big, but we know that it sits in this huge volume of dark matter. Our galaxy is 25 kiloparsecs from sort of end to end. So, you know, 250,000, let's just say very round numbers, 1 million light years across, ballpark. 10 times that is sort of where the density profile of dark matter is still well defined. So we still know dark matter is way outside of our own galaxy. So if the galaxy is defined as stars and light, well, maybe it's 50 kiloparsecs or something for an average sized galaxy like the Milky Way in width. But if you're saying, well, a galaxy is a dark matter, then it's 10 times out further than that. And when you're talking about galaxies at this level, you really want to know, like, you know, what's going to happen when these two galaxies collide. So you want to know where the dark matter potential really dips down to negligible. So it's an arbitrary definition. For our galaxy, you know, I would say we're 8.5 kiloparsecs out from the center. You could go out to 15 kiloparsecs and I'd still say you're part of the galaxy. But you can still go out 20 kiloparsecs and find these, what we call globular clusters, these little collections of stars that latched onto our galaxy probably billions of years ago through interactions. And they're still part of our galaxy because they're orbiting around the mass of our galaxy, but they're not really part of our galaxy because they may not have formed with the galaxy in the first place. So it becomes very fuzzy very quickly. But if you have 5 astronomers in a room, you're going to have 7 opinions on what the edge of the galaxy is. So I saw 3 hands go up. You have a question? There's no silly questions. Ask whatever question you want, because I say in class, if you're thinking it, there's 10 other people who are thinking the same question. So do you want to ask a question? No? Okay.
These boring red galaxies.
Yeah.
And I think of it being active, but are they like spider galaxy like the Milky Way and stuff?
So my whole dissertation, oh, okay. So the question is the boring galaxies, the red, what we call elliptical galaxies, what's happening with them? Are they actually doing anything at all? Or are they just collections of stars? I think is the gist of your question. Is something going to happen to these in the near future? And the answer is depends on who you ask. So they are quite active. So if I go back, I'll call out in the image here. I don't know if you can quite see this. There's this big red galaxy, but do you see that little streak there?
Yeah.
There's a little streak. This is M87. This is a cluster of galaxies. This is the most massive galaxy in a cluster of galaxies at which we sit on the outer outskirts of this cluster of galaxies in what we call the Virgo cluster, which is about 10 or 30 million light years away. These are technically our neighbors in local space. This galaxy looks very boring except for this little spark here. This is a jet of material that's traveling at 0.999 times the speed of light, almost the speed of light, and that's being ejected by a supermassive black hole, which has a mass 100 times larger than the mass of our supermassive black hole that sits at the center of our galaxy. And it is clearly feeding. It's doing something because it's producing this giant jet. So it must be accreting material onto it. It must be heating up as it falls in, produces radiation. That radiation gets collimated by magnetic fields probably, and then ejected back out to make this little, this is as big as our galaxy, this streak that we're seeing. I mean, it's a huge streak. Or the distance to the center of our galaxy. It's kiloparsecs long. And it's punching through all of the gas of the galaxy and heating it up as it goes along, and that's why we see it. But the massive black hole in the center is actively doing something. Now, this won't do much. The stars in this system will age over time. They'll, like our own sun, around the same time that we first start seeing Andromeda come close, our sun starts to burn out. In about 4 billion years, take your life insurance policy out now. In 4 billion years, all the oceans will be boiled off by the expanding sun as it moves into its red giant phase. Those stars there that are sun-like, they'll be doing the same thing in a few billion years. Eventually, there'll be fewer and fewer stars, and it'll end up being mostly just these brown dwarfs. The lowest mass stars will be the only stars that are actively fusing, which discriminates a star from a non-star. But they'll be mostly full of white dwarfs and old dead remnants of stars. There will be supernovae periodically, because sometimes they can collide. So there'll be flashes of light in this galaxy over the next 5 billion years to enjoy. But by and large, its life cycle is done. Now, the reason that we published this paper with these galaxies is it turns out when we look in the distant universe, when we find the same, what we call red and dead galaxies, the red and dead galaxies that we find in the high redshift universe, or the distant universe, most of them aren't doing anything interesting. They're red and they're dead. They're old sun-like stars and they haven't formed any new stars. But when you look at them in the ultraviolet, because we originally classify red based on the optical colors, what we see by eye, when you look at them in the ultraviolet, where only young stars, hot stars appear, it turns out about 15% of these galaxies still are actively forming stars, or have done so in the past billion years, which to an astronomer is a blink of an eye, okay? These galaxies are still actively forming stars, or very recently forming stars. So they still are doing something in many cases. They're not completely dead. And this is what I did my dissertation on. I had learned that there are red and dead galaxies and spiral galaxies, and ne'er should the two look similar to one another. And what we found is, when I started grad school in 2008, we did the Service Mission 4. We put a new camera that had ultraviolet capability on Hubble, and we looked at these objects in the ultraviolet. And sure enough, there were a lot of blue in the ultraviolet red galaxies. And when I did my dissertation, the guy who studied this in the 80s, who had passed away, the guy who really nailed down the life cycle of these galaxies in the 80s, he was at the university. He passed away before I did my dissertation, but all the faculty were with him. And the first hour of my defense was, are you really sure that these galaxies are red and dead? Because it's been taken as gospel that for a century, these galaxies weren't doing anything interesting at all. But that's the joy of having new telescopes, is you look at old objects or old ideas and you find out you really didn't understand them like you thought you did. And that changes everything about galaxy evolution, because now all of a sudden, these galaxies are still, why do they have young stars? Where did the gas come from? They don't have it in-house because they're too hot. They're dynamically hot. And so where did it come from? Well, if you want to do a PhD, do it with me. Look at these systems. They all seem to have little bits of crud floating around them. All of these objects may eventually fall in. If these are blue and they have lots of gas, maybe some of that gas ends up in that central galaxy, and poof, a few stars pop up, and for a brief moment in time we see them. So the best place to find a galaxy in the universe is next to another galaxy. And I thought, well, maybe those two things are related to give rise to this UV light that we couldn't explain otherwise. It took a long time to convince the Hubble TAC to fund this, but we submitted the proposal to do this large imaging survey 8 years in a row, and we finally got it. And the reason is because it was a full month of clock time on Hubble, and there's only 12 months in a year, and everybody's fighting for that same time. So, but now we did it, and now we have millions of other galaxies at high redshift to do the same thing. So we can still do this science with J2SG. Oh, question?
So in your timeline where you show what year we know how far back in time we measure, where would they show, oh, this is where Hubble James Webb allows us to move further back?
Yeah.
So where
So it's a multi-part question. We can go all the way back to this point of recombination. You all can see this now. If I turn off this TV and we put static, 1 in 100 of those static dots is coming from this period. It's a radio photon that smacks into the scintillating screen and causes a flare, a pixel to light up. We can see this in the radio, but there's no optical counterpart to this because it's too cold now. It's not warm enough to produce that radiation. In this period in between, there's neutral gas because no stars have formed. So you can detect neutral gas and hydrogen with radio telescopes. They do this now in South Africa. They do it in Australia. And there's a couple of different surveys, the Meerkat survey and the SKA survey, that's looking at what was the distribution of gas in the early universe before galaxies formed. So in the optical, you're limited to, at best, this. This is where JWST takes us. And probably it'll take us to the first galaxy. I don't know, but it'll take us pretty close. But beyond that, it's the radio. And if you want to do anything in this period, there were no atoms. There was no proton yet. In the first 4 minutes, there were no protons. So if you're looking for a signal associated with a proton oscillating in some electric field, you're never going to see it because the soup within which it's sat is too hot to allow that proton to stay there. So it's just pure energy. Now, with that said, there is potentially a gravitational wave signature associated with that because you still have mass. And the hope is, one of the big problems for astronomers is that, or cosmologists, people who study the universe as a system, we only have one universe. We only have one object to study. And so how do you, why is the charge of the electron the charge of the electron? Why did that come into be? Could you have other values of the charge of the electron and still have stable atoms? We don't have other universes to run that experiment in. And so one of the things that physicists are really excited about, less so astrophysicists, is probing this very early time to look for potential imprints of the pre-universe. I'm sure it happens, it's the Deus ex machina in every Marvel movie, that there's a parallel universe that you can travel through, and the superhero travels through space and time. We may not be the only universe out there. There may be multiverses in which the mass of the proton is slightly different or the charge of the electron is slightly different. That signature may be imprinted in, for example, a gravitational wave signal. Now, the problem is that we don't have a detector yet to nail that down, but there are certainly people who are working. This is one of the reasons to go back to the moon, for example. The Earth is really bright in the radio. We all listen to radio stations. We all have cell phones. We all have transmitters that are transmitting in the radio spectrum. If you go to the back side of the moon, so that the whole rest of the moon is blocking the Earth from your signal, if you build a giant radio telescope on the back side of the moon, you may be able to start teasing out what was hydrogen doing in this early time. Now, you say put a telescope on the moon, and people say, "Are you crazy? That's going to cost $1 trillion or something." So the first ideas for lunar-based observatories were 1960, and it's always been 20 years away. And so I don't know if it's ever going to happen. But physicists are really excited about that because it provides them access to a regime in which you can't make this soup at Thomas Jefferson. It's just, you can't get, the power bill for that is too high. You need the energy of the sun in a minute in order to produce conditions of the universe like this. And no matter how excited the taxpayers are to support Thomas Jefferson, no one's going to pay for the output of the sun in a minute when you have to run the air conditioning in the summer or something. So everybody else wants AC first. But we give and take. I've often said that ultraviolet. The reason I'm an ultraviolet astronomer and so enamored with NASA is because we have an ozone. The ozone, thankfully, shields us from all the ultraviolet radiation of the universe. But if I want to study the ultraviolet, that means I have to go beyond the Earth. And the only person who goes beyond the Earth is NASA. NASA is the only people who are capable of putting rockets with billion-dollar observatories in Earth orbit or beyond. And I've often said, you know, you can pay for a billion-dollar telescope, or we can remove the ozone on the Earth. That's the only way we're going to make progress on this. And if you're not a fan of skin cancer, then option B is out. So let's try to figure out a way to launch a telescope instead. So one.
I don't know. When I was in the 7th grade, I learned about the steady state and the Big Bang. Big Bang won out. And I just recently read that there's evidence that some kind of, that maybe the universe is going to collapse.
Yeah.
And coming in on itself again.
So I skipped all this to stay only 30 minutes over my allotted time, but let's go here. This is a diagram. This is the reason we built Hubble. This is what we call the Hubble diagram, or Hubble plot, Hubble figure, the Hubble law. When Hubble first made his measurements of the distances of galaxies, he also measured how fast they were expanding away from us, or moving away from us. And what he realized is that the further away you looked, the more distant galaxy you observed, the faster they were moving away. And so this looks exactly like, I won't go through the math because I know people are leaving already, but this looks exactly like what you would expect if like a bomb were to explode and you were to measure the recession velocity of the shrapnel from the bomb moving out from that center point over time. The farther you look out, if you start the bomb exploding at time equals 0, after a minute, the stuff that's closest into the site of the explosion must be moving slower than the stuff that's a mile down the road, because they all were traveling, they all were released at the same time. Oh, sorry. I have to back up. The question was, for the record, was what's going to happen to the universe? Is it going to steady state? Is it going to collapse on itself? Will it expand forever? What have you? So what Hubble discovered is that it is expanding. And for a long time, that was the working model. But the reason that the steady state theory existed, or the steady state idea, the idea that it's just we're just going to continue expanding forever, but the reason that was debated was because there's another idea that if you put mass in the universe, like galaxies and clusters of galaxies, that material is gravitationally attractive. And over time, depending on the balance between the rate of expansion and the attraction of galaxies, which are going to pull on the space-time in which they sit on large, large scales, it may be the case that the universe doesn't actually keep expanding forever, but it actually starts to contract in on itself. And we have like a big crunch, we used to call it. But then something happened in 1998 with Hubble, where Adam Rees and friends applied Hubble to look for the most distant objects to make the best observation of the expansion rate of the universe. And this figure looks kind of similar, but it's very different in a key way. So these are more distant objects further out. And this is how much further away would the object appear given our theory of the steady, sort of a steady expansion rate as predicted by Hubble. And what you'll notice is that close in, the models aren't, you can't discriminate the different models. But as you move to galaxies that are further and further out, the data tend to cluster on one side of the diagram instead of the other. Which means these objects, if you're on this side of the diagram, what Adam observed is that those galaxies in the very distant universe appeared to be farther away than you would predict if the universe was expanding as Hubble said it was expanding in the 1930s. How do you get something further away than you expect? At some point in the history of the universe, something had to accelerate the expansion. If you're traveling behind in a carpool and you're both going 60 miles an hour for an hour, you're both going to be at the same distance away an hour later because you're traveling the same speed. But if you look back and the person is now 2 miles behind you, they must have decelerated from 60 miles an hour to something slower in order to get that larger distance. That's basically what this plot indicates. And he won the Nobel Prize for this because the only thing that we could come up with that would cause the universe to expand was the thing that I didn't mention, but it must be an extra energy term in the universe's expansion. We can't see it. There's no evidence of what it is, so it's dark. And we already use dark matter, so and it's repulsive, not attractive like matter is, so we call it dark energy. And now the theory is that dark energy started to accelerate about the time that the universe, or our solar system came into existence, 4.5 billion years ago. This acceleration began, and there's no reason why it wouldn't continue in the present form. And we're in something like, I don't want to give you the exact number because I don't have it on the top of my head, but on the order of tens of billions of years, the entire universe we're going to observe is just going to be our Milky Way galaxy, because the universe will have accelerated away. We are at the prime time for the next 10 billion years. We got to do all the astrophysics we possibly can, because in 100 billion years, we're not going to know there's the rest of the universe out there. That early universe that I said we could probe with high energy physics, that won't be visible. It'll have been accelerated out of the light travel distance that we are able to detect in the universe in which we live in. We'll never know it's there. So we're living at a special time in the universe, and our best bet is that it'll continue expanding, and it's going to accelerate in expansion. Now, with that said, 2 weeks ago, we just found evidence that dark energy doesn't seem to be causing the acceleration at a constant rate. So there's another term in there, and that gives us hope, because maybe that'll help us understand what the heck is this term in this equation that Einstein threw in, and he really wanted to erase it, but he threw it in to make everyone else around him happy with his new field equations in general relativity. And then Hubble made the discovery, and he erased it, and he said, it was his biggest blunder. In order to make the universe work like the universe that was observed after Hubble discovered the expansion rate, he took it out. And then we realized, no, it really has to be in the equation. So 80 years later, they put it back in, and this is that dark energy, the lambda constant, which may not be as constant as we think, but that's only hit the presses in the past 2 weeks, so I can't tell you much more than that. Anyway, well, thanks for sticking with it. So, I think we went a little over.
No, just a smidge, just a smidge. Thank you so much.
Oh.
That just blew my mind. I think it always reminds me that we were very trained, and we really just stuck. So thank you again. If you guys are interested in learning a little bit more about our universe, and you've never been out to visit us in our planetarium, definitely come check that out on the second Saturday of every month. We do some stargazing, if the weather permits. So we can come and hopefully get a glimpse of things that we might not be able to get a glimpse of much longer. If you enjoyed our speaker series tonight, please come back next month on May 15th. We are going to be talking about the ecology of ticks. We're making a big right turn. So, thank you guys. Have a wonderful evening. Drive safe, and we'll see you again soon.
Yep.